Hello everyone, my name is Tian Xia. For my project, my advisors are Bo Fang and Kai Zhu. And welcome to this demonstration of the perception model using a Jupyter notebook. Today, I'm going to guide you through how the perception works, focusing on how it updates its weights during training, and I'll visualize the decision boundary for both successful and failed cases. To begin, the perceptron is one of the simplest types of neural networks. It works as a binary classifier that tries to learn a linear decision boundary that separates data points into two classes. In this notebook, we'll look at three datasets: an OR gate, an AND gate, and an XOR gate, to see how the perceptron learns in each case. Let's start with the OR gate dataset. Here, the perceptron tries to learn the relationship between inputs and outputs. We have two input features, and the output is 1 if at least one of the input is 1, otherwise it's 0. We initialize the perceptron with 0 weights and a bias of 0. During each iteration, the perceptron updates its weights if it makes an incorrect prediction. The weight update rule is quite simple. The weight is adjusted by a factor proportional to the learning rate, the input feature, and the difference between the actual label and the prediction. This way, the perceptron progressively corrects its decision boundary until it can classify the training points accurately. In the case of the OR gate, since the data is linear separable, the perceptron is able to successfully learn the correct decision boundary. Now, if you take a look at the decision boundary for the OR gate after training, you can see how it cleanly separates the two classes. The points where either input is 1 are classified as one group, and the point where both inputs are 0 is classified as the other. This visual representation gives us an intuitive understanding of how the perception works. Next, we'll train the perceptron on an AND gate dataset. In the AND gate, the output is only 1 if both inputs are 1. Similar to the OR gate, the perceptron starts with initial weights and bias, and updates them whenever it makes a wrong prediction. This time, we are also tracking the decision boundary after each epoch to see how it evolves during training. As you can see from the visualizations, the decision boundary gradually moves to separate the classes correctly. By the end of training, the perceptron successfully learns the decision boundary that classifies the points correctly for the AND gate. The progressive plots give a clear picture of how the decision boundary gets refined step by step. Now let's move on to the XOR gate dataset. The XOR gate is more challenging because its data is not linear separable. The output is 1 only if the inputs are different, and 0 if they are the same. Unlike the OR and AND gates, no straight line can separate the classes of the XOR dataset. Here, as we train the perceptron on the XOR gate, we can see that it struggles to find a suitable decision boundary. The perceptron keeps updating its weights, but it never reaches a point where it can correctly classify all the data points. This is because the XOR data requires a non-linear decision boundary, which the simple perception model cannot provide. The resulting decision boundary visualization shows that the perceptron fails to accurately separate the classes, leaving some misclassifications. To summarize, we've seen how the perceptron updates its weights during training and how it can effectively learn linear decision boundaries, as demonstrated with the OR and AND gate examples. However, the perceptron is limited to linearly separable problems, as evidenced by its failure to classify the XOR dataset correctly. This limitation led to the development of more advanced neural networks that can handle non-linear decision boundaries. I hope this demonstration has helped you understand how the perceptron works, how it learns, and where its limitations lie. Thank you for watching.